On January 7th, the Hubble Space Telescope captured something that shouldn't exist. 3I Atlas, a visitor from interstellar space, is doing impossible. Material is streaming toward the Sun, not away from it, toward it, and nobody can quite explain why. Stay with me. In the next few minutes, we're going to uncover what Hubble's latest images reveal about this mysterious object, why it's breaking every rule we thought we understood about comets, and what this cosmic anomaly tells us about the universe beyond our solar system. For centuries, astronomers have watched comets dance through our sky, and they all follow the same fundamental pattern. Their tails always point away from the Sun, pushed outward by solar wind and radiation like cosmic windsocks, showing which way the storm blows. Always away, never toward. It's one of those rules you could stake your career on, one of those constants that textbooks treat as absolute. And yet here we are, looking at images that seem to mock that certainty. The object designated 3I Atlas, an interstellar wanderer passing through our solar neighbourhood, is displaying a brilliant jet of material that appears to stream directly toward the Sun. It cuts through space like an arrow pointing at our star, defying logic and physics in a single frozen moment captured by humanity's most famous orbital telescope. This isn't a trick of light or a processing error. Hubble's instruments don't make mistakes like that. The images are clear, sharp, and utterly bewildering. Scientists have reviewed them multiple times, checked the calibrations, confirmed the coordinates, and verified the timestamps. Everything checks out. The data is solid. And the data shows something that challenges our understanding of how objects behave in space. If you've been following this channel, you know that 3I Atlas has been on our radar since it first appeared as a faint smudge in distant telescope images. We've watched it brighten as it made its closest approach to the Sun in late October, tracked its unusual orbit, and marvelled at its interstellar origin. But these latest Hubble observations have elevated this object from interesting curiosity to profound mystery. What Hubble captured goes beyond the strange trajectory or unusual composition. It goes to the heart of how we understand cometary behaviour, solar influence on small bodies, and perhaps even the fundamental differences between objects born in our solar system and those that formed in the darkness between stars. Before we dive deeper into what makes this sunward jet so bizarre, I want to ask something of you. If this cosmic mystery has grabbed your attention the way it's grabbed mine, hit that like button right now. And if you're the kind of person who loves unravelling the universe's secrets one discovery at a time, subscribe to this channel, because we're going to follow this story wherever it leads. Drop a comment telling me where you're watching from, and whether you think there's a simple explanation for what we're seeing, or if 3I Atlas is genuinely rewriting our understanding of interstellar visitors. Your perspective matters, and this discovery belongs to all of us who look up and wonder. Now, let's talk about what Hubble actually saw. The image itself is striking even before you understand the implications. Against the black backdrop of space, 3I Atlas appears as a bright nucleus surrounded by a fuzzy coma of gas and dust. This is typical comet behaviour, nothing unusual there. The Sun's heat causes ices on the surface to sublimate, releasing gas and carrying dust particles along with it, creating that characteristic fuzzy appearance that gives comets their name. The word comet comes from the Greek for long-haired, describing the appearance of these objects as they streak across our sky with their flowing tails trailing behind them. But look closer at the Hubble image. Look past the nucleus and the coma. There, extending from the central region, are distinct streams of material. Not just one, but 3 separate jets, each pointing in different directions. And one of them, the most prominent and puzzling, extends in a direction that appears to point back toward the Sun. It's visible as a narrow, elongated feature cutting through space with geometric precision. The jet doesn't curve or diffuse the way you'd expect from random outgassing. It maintains its structure, its direction, its impossible orientation. When the first researchers examined these images in detail, there was a moment of collective confusion. They checked the orientation of the spacecraft, verified which direction the Sun actually was relative to 3I Atlas, and confirmed that yes, This jet really does appear to point sunward. Then came the rapid consultations, the pulling up of theoretical models, the searching through databases of previous observations to find any comparable case. Because this doesn't happen. Comet tails don't point toward the sun. It's not a thing. It's like watching water flow uphill or seeing smoke descend into a campfire. The universe doesn't work that way, except, apparently, sometimes it does. Or at least, it appears to. And that distinction between appearance and reality is where this mystery gets truly fascinating. Because while the initial images seem to show material streaming toward the sun, the actual physics are almost certainly more complicated than that simple description suggests. Space is three-dimensional, and our view from Earth or from Hubble's orbit gives us only one perspective on objects that exist in that full three-dimensional environment. Geometry matters. Angle matters. The direction we're looking matters enormously when trying to interpret what we're seeing. But even accounting for perspective and geometry, even acknowledging that our line of sight might create optical illusions, the jet captured in Hubble's images remains deeply unusual. Scientists who specialize in cometary physics have spent years studying how these objects behave, mapping the patterns of their outgassing, understanding the forces that shape their tails and jets. They've developed sophisticated models that predict, with remarkable accuracy, how comets will look as they approach the sun, how their activity will increase, how their tails will form and evolve. Those models are based on thousands of observations of hundreds of comets. They work, they're reliable, and none of them predicted what we're seeing in these latest images of 3I Atlas. The triple jet pattern itself is noteworthy. Comets often display jets, localized areas of enhanced outgassing caused by more active regions on their surface. As the nucleus rotates, these active areas turn toward the sun and heat up, releasing bursts of gas and dust that create visible jets extending from the comet. Think of them like geysers on a rotating world, each one erupting when it faces the warming influence of our star. Many comets show multiple jets, and that's not surprising given their irregular shapes and varied surface compositions. But the geometric arrangement visible in the Hubble images, the specific angles and orientations of the three distinct jets emanating from 3I Atlas, creates a pattern that's statistically rare. One jet extends in what we might call the normal direction, away from the sun, following the expected pattern we've observed countless times before. Another extends at an angle, creating a curved arc as the dust particles it contains respond to solar radiation pressure over time. These two jets, while interesting, don't challenge our understanding of cometary behaviour. They fit the models. They make sense within the framework we've built from decades of observation and study. But that third jet, that sunward-pointing stream of material, that's the one keeping researchers up at night, the one generating heated discussions in astronomy departments, the one that makes you question whether we really understand these ancient wanderers as well as we thought we did. It extends from the nucleus with remarkable clarity, a defined structure that speaks to organised forces at work rather than random processes, and it points unmistakably in a direction that seems to defy the fundamental rules governing how matter behaves in the sun's domain. What makes this even more compelling is the timing. These Hubble observations came as 3 Atlas continues its journey through our solar system, approaching its closest point to the sun. Activity was near its peak during its closest approach in late October, and these January observations captured the comet while still significantly active during its outbound journey. Scientists had planned these observations carefully, knowing that this would be the optimal time to study this interstellar visitor in detail. They expected to capture spectacular images of a comet in full display. They got that, certainly, but they also got a puzzle that nobody anticipated. The images represent hours of careful observation, Hubble's instruments locked onto this distant target, tracking its motion through space, gathering photons that travelled across the solar system to paint this portrait of impossibility. Every pixel contains information, Every shade and brightness variation tells part of the story. And the story those pixels tell is one of an object that doesn't quite fit our expectations, that behaves in ways both familiar and utterly strange, that reminds us how much we still have to learn about the cosmos beyond our small planetary home. So we're left with questions that demand answers. What exactly are we seeing in these images? Is this truly material streaming toward the sun? Or is there a more subtle explanation involving viewing geometry and three-dimensional structure? Why does 3i Atlas display this pattern when countless other comets don't? What does this tell us about the object's composition, its internal structure, its history travelling through the galaxy before entering our solar system? And perhaps most intriguingly, does this behaviour reveal fundamental differences between objects born in our solar neighbourhood and those that formed in entirely different stellar environments, shaped by different conditions, carrying different chemical signatures, behaving according to rules we haven't fully documented yet? The impossible discovery captured by Hubble on January 7th isn't just about one comet doing something strange. It's about the moment when our confident understanding meets cosmic reality and realises there are still secrets to uncover, still phenomena to explain, still mysteries written in ice and rock and ancient starlight waiting for us to decode them. And that realisation, that acknowledgement of how much remains unknown, might be the most exciting discovery of all. Before we can truly appreciate how strange that sunward jet is, we need to understand the rules it's breaking. And that means talking about solar wind, radiation pressure, and the fundamental forces that govern how comets behave when they venture into the inner solar system. Don't worry, I'm not going to drown you in equations or technical jargon. Instead, think about something familiar. Think about holding your hand out of a car window on the highway. Feel that pressure against your palm, that force pushing your hand backward. That's what moving air does. It exerts pressure. It pushes things. Now imagine that instead of driving through air at highway speeds, you're a comet moving through space at thousands of miles per hour toward or away from the sun. And instead of air molecules hitting you, it's a constant stream of charged particles blasting outward from the sun at over 1 million miles per hour. That's solar wind. It's not gentle. It's not subtle. It's a hurricane that never stops. A cosmic gale that fills the entire solar system with invisible force. When a comet approaches the sun and warms up, its surface ices start to vaporize. Water ice, carbon dioxide ice, methane ice, all the frozen volatiles that make up these ancient objects, begin to transition directly from solid to gas. This outgassing carries dust particles along with it, creating the coma around the nucleus and eventually forming the tail. But here's the crucial part. The gas and dust don't just drift randomly in space. They immediately encounter that solar wind, that relentless stream of particles flowing outward from the sun, and they get pushed, driven, forced away from the sun with tremendous power. There's another force at work too. Radiation pressure. Sunlight isn't just light, it's electromagnetic radiation-carrying momentum. When photons from the sun strike dust particles in a comet's coma and tail, they transfer that momentum, physically pushing the particles away from the sun. For tiny dust grains, radiation pressure can be incredibly effective, sometimes even more powerful than solar wind. The smaller the particle, the more surface area it has relative to its mass, and the more effectively radiation pressure can push it. So you end up with this beautiful effect where the finest dust gets blown away from the sun most efficiently, creating those sweeping, curved dust tails that can stretch for millions of miles across space. The combination of solar wind and radiation pressure creates an iron law of cometary behaviour. Tails always point away from the sun. Not sometimes, not mostly, always. If you see a comet in the night sky, you can determine which direction the sun is simply by looking at which way the tail extends. Point your finger along the tail away from the comet's head, and you're pointing away from the sun. It's one of the most reliable, consistent, predictable phenomena in observational astronomy. Generation after generation of astronomers have relied on this rule. It's in every textbook. It's taught in every introductory astronomy course. It's as fundamental as gravity. And it's not just terrestrial prejudice or limited observation. We've sent spacecraft to comets, studied them up close, mapped their surfaces, sampled their tails, and measured the forces acting on them. Every single close-up examination has confirmed what telescopic observations suggested. Solar wind and radiation pressure dominate the motion of gas and dust once it leaves the nucleus. The sun's influence is absolute. Material flows away, not toward. Think about what this means for a moment. Every comet that's ever approached the sun in the entire history of our solar system has followed this pattern. 4.5 billion years of comet behaviour, billions upon billions of individual passages through the inner solar system, and every single one has displayed tails pointing away from the sun. The statistical consistency is staggering. It's not just a strong trend or a general rule. It's a law enforced by physics itself, by the fundamental interactions between radiation, charged particles, and matter. So when scientists looked at those Hubble images and saw a jet apparently pointing toward the sun, their first instinct was to find the error, check the orientation data, verify the pointing coordinates, confirm that the telescope was aimed correctly and that the processing software hadn't flipped the image somehow. Because the alternative, that they were genuinely seeing material streaming toward the sun, would require rewriting basic physics. And physics doesn't get rewritten lightly. It takes extraordinary evidence to overturn ordinary understanding. But the data checked out. The orientation was correct. The image processing was standard. There was no error, no glitch, no simple explanation that made the impossible possible go away, which meant confronting the reality that 3i Atlas was doing something comets aren't supposed to do, or at least appearing to do something they aren't supposed to do, and that distinction matters enormously. Here's where it gets interesting in a different way. Space is three-dimensional, but we observe it from essentially a fixed viewpoint. Earth orbits the sun, and Hubble orbits Earth, which gives us some change in perspective over time. But in any single observation, we're looking at objects spread through three-dimensional space, projected onto a two-dimensional image. It's like trying to understand the full shape of a building from a single photograph. You can see some of its structure, but angles and depth can create misleading impressions. Imagine a comet with material streaming away from the sun in all directions, creating a spherical cloud of gas and dust. Now imagine that some of that material, instead of being blown directly backward by solar wind, gets ejected from the nucleus in a different direction first. Maybe an active region on the side of the nucleus, facing away from the sun, releases a burst of gas and dust. That material initially travels away from the nucleus in that direction, sideways or even forward relative to the comet's motion. But immediately, solar wind and radiation pressure start pushing it. Over time, it curves, bends, follows a trajectory that's a combination of its initial velocity and the forces acting on it. From certain viewing angles, this could create the appearance of material pointing toward the sun, even though the actual motion of every particle is ultimately away from the sun when you measure it in 3 dimensions. It's geometry, perspective, the same optical effects that can make parallel railroad tracks appear to converge in the distance, even though they never actually meet. Our brains interpret two-dimensional images and sometimes get the 3-dimensional reality wrong. So one possibility, the one that doesn't require rewriting physics textbooks, is that 3i Atlas is displaying what astronomers call an antitail. This is a well-documented phenomenon, though it's rare enough that many comet observers go their entire careers without seeing a clear example. An antitail isn't material actually moving toward the sun. Instead, it's a geometric projection effect created by large dust particles. that don't get pushed away from the Sun as efficiently as smaller particles. These bigger grains follow the comet's orbital path more closely, spreading out along the orbit in both directions from the nucleus. When Earth and the comet are positioned just right relative to each other, we can see this sheet of orbital debris edge on, and it appears as a spike or jet extending toward the Sun. It's similar to how Saturn's rings almost disappear when we view them edge on. The rings are still there, still orbiting Saturn, but from certain angles we're looking at their thin edge, and they appear as just a line across the planet rather than the magnificent structures we see when we have a better viewing angle. An antitail works the same way. We're seeing a disk or sheet of debris edge-on, compressed by perspective into a narrow line that can point in any direction depending on the geometry, including toward the Sun. This explanation has the benefit of not breaking physics. Solar wind and radiation pressure still behave exactly as we expect. Material is still flowing away from the Sun. We're just seeing a perspective effect that makes it look like something different is happening. Many astronomers, upon seeing the Hubble images, immediately suggested that an antitail must be the explanation. It fits the data. It preserves our understanding of cometary behaviour. It's the conservative interpretation that doesn't require us to reconsider fundamental principles. But here's what keeps this from being a completely satisfying answer. Antitails are rare precisely because the geometry has to be very specific. The orbital debris has to be distributed in a particular way, we have to be viewing it at the right angle, and the effect is usually subtle and short-lived as the geometric alignment changes with the comet's motion. What Hubble captured doesn't look subtle. It looks prominent, defined, structured. The jet is narrow and extends a considerable distance from the nucleus. It has features, variations in brightness along its length, characteristics that suggest it's more than just a sheet of debris seen edge-on. Moreover, 3I Atlas is special in another way that we haven't fully addressed yet. It's not from our solar system. This object formed somewhere else, in orbit around another star, shaped by different conditions, composed of materials that might have different properties than the ices and rocks we're familiar with from studying solar system comets. What if interstellar objects don't behave exactly like their local cousins? What if there are subtle differences in composition or structure that create behaviours we haven't seen before, simply because we've never had the chance to study an interstellar comet in detail? That's the tension sitting at the heart of this mystery. Do we interpret what we're seeing through the lens of familiar physics and familiar phenomena, finding explanations that fit our existing models? Or do we allow for the possibility that this visitor from beyond is teaching us something new, revealing behaviours that our models don't account for because they've never needed to? Both approaches have merit. Both are part of how science progresses, balancing healthy skepticism with openness to genuine novelty. And right now, looking at those Hubble images, the scientific community is actively debating which interpretation better fits the evidence. That's the beautiful mess of discovery in action, the process of refining understanding through observation and argument and testing predictions against reality. The rules of space aren't truly being broken, but they might be more complicated than we realised, with exceptions and edge cases that only become visible when we study objects like 3I Atlas, rare visitors that don't fit neatly into our existing categories. Now let's talk about something that takes this mystery to an entirely different level. Because that sunward-pointing jet, as bizarre as it appears, isn't even the strangest part of what Hubble captured. Look at the complete image. Look at the full structure surrounding 3I Atlas. There aren't just one or two jets. There are three distinct streams of material, each pointing in different directions, each with its own character and behaviour, and together forming a pattern that makes astronomers deeply uncomfortable, because patterns like this aren't supposed to exist. The human brain is exquisite at recognising patterns. It's one of our greatest evolutionary advantages, this ability to spot structure in chaos, to see organisation where randomness might reign. Sometimes that ability leads us astray, making us see faces in clouds or hear messages in static. But sometimes it reveals genuine structure, real organisation that demands explanation. And when multiple scientists, trained to be sceptical of pattern recognition, all look at the same image and see the same striking geometric arrangement, it's worth taking seriously. The 3 jets emanating from 3I Atlas aren't randomly distributed around the nucleus. They're spaced at regular intervals, creating angles that suggest symmetry. Imagine looking down at the comet from above its north pole. You'd see these 3 jets extending outward, like the hands of a clock pointing to different hours, distributed around the nucleus with geometric precision. One points in what appears to be the sunward direction. Another extends away from the sun, more or less following the expected pattern. The third occupies a position between them, creating this triangular arrangement that's visually striking and scientifically puzzling. Why would a comet produce jets in this specific configuration? To understand why that's such a good question, we need to think about what causes jets in the first place. A comet nucleus isn't a uniform ball of ice. It's an irregular chunk of frozen material, shaped by its formation billions of years ago and modified by countless passages near stars, perhaps even by collisions with other objects during its long journey through the galaxy. The surface is almost certainly varied, with different regions having different compositions, different icy-to-dust ratios, different thermal properties. When sunlight hits this irregular surface, some areas heat up more effectively than others. Maybe they have a higher concentration of ice. Maybe they're oriented more directly toward the sun. Maybe they have less dust covering the ice, allowing sunlight to penetrate more easily. Whatever the reason, these active regions produce more outgassing than their surroundings. As the nucleus rotates, an active region turns toward the sun and heats up, producing a jet of gas and dust that streams away from that location. The jet persists as long as the active region remains illuminated, then fades as rotation carries it into shadow. This is well understood. We've observed jets on many comets, studied their behaviour, mapped their source regions. What's not well understood is why 3I Atlas would have 3 active regions arranged in this particular geometric pattern. Random processes don't produce regular spacing. Chaos doesn't organise itself into neat angles. When you see structure, when you see symmetry, it usually indicates some underlying physical principle at work, some organising force or constraint that shapes the outcome. One possibility involves the nucleus rotation. If 3I Atlas is spinning in a particular way, and if it has a shape that's not quite spherical, the combination of rotational dynamics and solar heating could potentially create a pattern of active regions. Think of how a figure skater pulls their arms in to spin faster, or extends them to slow down. Rotation and shape interact in complex ways. For an irregular object like a comet nucleus spinning through space while being heated unevenly by the sun, the physics gets complicated quickly. Maybe those complications produce patterns we wouldn't intuitively expect. But even granting that rotation and shape could create organised jet patterns, the specific arrangement visible in the Hubble images is statistically unusual. Scientists have catalogued jets from hundreds of comets. They've watched how these jets appear and disappear, how they change with rotation and with distance from the sun. And while some comets certainly show multiple jets, the kind of regular spacing we're seeing with 3I Atlas is rare. It's the kind of thing that makes you wonder whether there's something special about this object's structure or composition. Something we wouldn't know to look for, because we've never studied an interstellar comet in this kind of detail before. Each of the 3 jets also has its own distinct characteristics. They're not identical streams of material. They have different brightnesses, different lengths, different apparent widths. One is sharp and well-defined, maintaining its structure over a considerable distance from the nucleus. Another is more diffuse, spreading and fading more quickly. The third, that troublesome sunward-pointing feature, has an appearance that's different still, with variations along its length that suggest complex processes at work. This variation tells us something important. It means the three jets aren't simply the result of the same process happening in three different locations. If they were, you'd expect them to look more similar to each other. The differences in appearance suggest differences in the source regions, in the material being released, in the forces shaping each jet's evolution. One active area might be producing more dust relative to gas, another might be ejecting material with higher velocity, a third might be located in a region where the surface has different thermal properties, causing it to behave differently under solar heating. Reading these subtle variations is like reading a story written in gas and dust, a narrative about what's happening on and beneath the surface of this ancient object. Every difference in brightness, every variation in structure, every detail in how the jets appear and evolve contains information. The challenge is decoding that information, translating visual observations into physical understanding. It's detective work on a cosmic scale, piecing together clues to understand what's really happening hundreds of millions of miles away. The geometric arrangement also raises questions about the nucleus itself. We don't have resolved images of 3I Atlas's nucleus. It's too small and too distant for even Hubble to capture its shape directly. We see the coma and the jets, but the solid body at the centre remains below the resolution limit of our instruments. That means we're inferring properties of the nucleus from its effects, from what it does, rather than what it looks like. It's like trying to understand what someone looks like from their shadow. You can make educated guesses, but you're working with limited information. If the nucleus is elongated, shaped more like a potato than a sphere, that could influence how jets are distributed. The longest axis might heat up differently than the shortest axis. Rotation around different axes creates different patterns of solar illumination. Shape matters enormously for these small bodies, affecting everything from how they rotate to how they respond to solar heating. And we simply don't know what shape 3I Atlas has. We can make educated guesses based on the behaviour we observe, but we're fundamentally limited by the fact that we can't see the object directly. There's another layer to this puzzle that makes it even more intriguing. The jets aren't static. They're changing as 3I Atlas continues its approach toward the Sun. Early observations showed different patterns than what we're seeing now. The relative brightness of the jets has shifted. New features have appeared while others have faded. This evolution tells us that we're watching dynamic processes, that the comet's behaviour is responding to changing conditions as it moves through different regions of the solar system. This temporal evolution is both helpful and frustrating. Helpful because watching how something changes over time provides information you can't get from a single snapshot. Frustrating because it means that any explanation we develop has to account not just for what we're seeing now, but for how we got here from what we saw before. The jets didn't simply turn on at their current configuration. They evolved, changed, adapted as the comet's environment changed. That evolution is part of the story, and any complete explanation needs to include it. The challenge facing researchers right now is building a model that explains everything, not just the sunward-pointing jet, though that's certainly the most visually striking feature, not just the triple jet pattern, though the geometric arrangement demands explanation, but all of it, the specific angles, the different characteristics of each jet, the evolution over time, the changes in activity level, everything we've observed from this object since it first appeared in our telescopes. That's the standard science demands. Explaining one feature while ignoring others isn't enough. The explanation has to be comprehensive, accounting for all the observations we have. Several research groups are working on exactly this problem right now. They're building computer models of comet nuclei, simulating how rotation and shape affect outgassing, calculating how jets would appear from different viewing angles, trying to reproduce what Hubble saw by adjusting parameters in their simulations until the output matches the observations. It's painstaking work, requiring deep knowledge of thermodynamics, orbital mechanics, gas dynamics, and radiative transfer. Each parameter you change affects multiple aspects of the output, so finding a configuration that matches all the observations simultaneously is like solving a multi-dimensional puzzle where every piece is connected to every other piece. And there's always the possibility, the tantalizing and slightly unsettling possibility, that no combination of standard parameters will match what we're seeing, that the models built from studying solar system comets don't quite apply to this interstellar visitor, that there's something genuinely different about 3I Atlas that requires expanding our theoretical framework to accommodate behaviours we haven't encountered before. This is how science progresses, through exactly these kinds of challenges. An observation that doesn't fit existing models either reveals an error in the observation or an incomplete understanding in the models. And right now the observation looks solid, which suggests the models might need refinement. The triple jet mystery isn't just a curiosity. It's a window into the fundamental question of whether objects from other stellar systems behave the same way as objects formed in our own. We've spent decades studying solar system comets, building our understanding from those observations. But what if that understanding is incomplete, shaped by the limited sample we've had access to? What if comets can behave in ways we haven't seen simply because all our observations until now have been of a specific subgroup, objects formed under similar conditions in the same stellar environment? 3I Atlas gives us a chance to test that assumption, and the test results so far suggest that maybe, just maybe, our textbooks need some new pages written, accounting for behaviours that only become visible when we expand our perspective beyond our local cosmic neighbourhood. Let me take you behind the scenes of how these images came to exist, because there's something profoundly human about the moment of discovery, about the process of pointing humanity's most famous telescope at a specific target and waiting to see what secrets it reveals. The Hubble Space Telescope doesn't just take pictures randomly. Every observation is carefully planned, scheduled months in advance, competing with thousands of other requests from astronomers around the world, who all want time with this incredible instrument. Getting approved for Hubble time is a significant achievement. It means convincing a review committee that your scientific question is important enough, that Hubble is the right tool to answer it, and that the observation you're proposing will yield valuable data. For 3I Atlas, that case was easy to make. Here was an object visiting our solar system from interstellar space, the third confirmed interstellar object ever detected, following Oumuamua in 2017 and 2I/Borisov in 2019. The opportunity to study it wouldn't last. Comets don't wait around. They follow their orbits relentlessly, appearing for a brief window when they're close enough to observe in detail, then vanishing back into the darkness. If we wanted to understand this visitor, if we wanted to capture data that couldn't be obtained any other way, Hubble was the tool for the job. Its position above Earth's atmosphere means it can achieve image clarity impossible from ground-based telescopes, no matter how large or sophisticated they are. Atmospheric turbulence, the phenomenon that makes stars twinkle, blurs telescope images. Hubble doesn't have that problem. It sees with crystalline clarity. The observation was scheduled for January 7th, time to catch 3I Atlas as it continued its journey outward, having passed perihelion in late October, but still displaying significant activity. The planning involved calculating exactly where the comet would be at the observation time, pointing Hubble at those coordinates, and locking the telescope's guidance system onto the target. This sounds simple, but remember that Hubble is orbiting Earth at thousands of miles per hour. Earth is orbiting the Sun, and the comet itself is moving rapidly through space. The pointing calculations have to account for all these motions, predicting not where the comet is now, but where it will be when the observation happens, and compensating for Hubble's own motion to keep the target centred in the field of view. The specific instrument used was Hubble's wide-field camera, the telescope's main imaging workhorse. This camera doesn't work like a regular camera in your phone. It's a sophisticated scientific instrument that can capture images in different wavelength bands, essentially taking pictures in different colours of light to reveal different kinds of information. For observing comets, astronomers typically use filters that highlight specific emission lines from molecules in the coma, or broadband filters that capture reflected sunlight to show the dust distribution. Each filter choice reveals different aspects of the comet's composition and behaviour. The observation itself took place over a period of time, not just a single snapshot. Hubble captured multiple exposures, building up light to reveal faint features, and taking images through different filters to gather maximum information. Each exposure has to be long enough to collect sufficient photons to create a clear image, but not so long that the comet's motion blurs the details. It's a balance, and the exposure times are carefully calculated based on the comet's expected brightness and motion rate. Then came the data transmission. Hubble doesn't store its observations long term. It takes images and then beams them down to ground stations when it passes over them during its orbit. The raw data files are transmitted to the Space Telescope Science Institute in Baltimore, where they're processed, calibrated, and made available to the astronomers who requested the observation. There's always a moment of anticipation in that process, waiting to see whether the observation succeeded, whether the pointing was accurate, whether the comet showed the features you hoped to capture. And sometimes the images exceed expectations in unexpected ways. When the processed images arrived and researchers pulled them up on their screens, the first reaction was probably excitement at the quality. The images were sharp, the comet's coma was clearly visible, the overall morphology was well captured. Success. The observation worked. But then, looking closer, examining the structure around the nucleus, they would have started noticing the details, the jets, the specific patterns, and that peculiar feature extending in an impossible direction. You can imagine the moment, someone zooming in on that sunward jet, checking the image orientation indicator to confirm which direction the sun actually is, feeling that mixture of confusion and excitement that comes when data doesn't match expectations. There would have been quick consultations with colleagues, pulling up the images on multiple screens, pointing out the feature to others, asking if they're seeing what you're seeing. Then the verification phase begins, checking the telescope pointing data to make sure Hubble was aimed correctly, reviewing the image processing to ensure no artifacts were introduced, comparing with previous observations to see if similar features appeared in earlier data. Every step confirms that the observation is genuine, that what you're seeing is real and not some technical glitch. This is the texture of scientific discovery. It's not just the eureka moment, though those exist. It's the careful process of verification, the systematic elimination of error sources, the building of confidence that what you're observing is truly a property of the object you're studying, and not an artifact of your instruments or methods. And it's the growing realization that you're looking at something genuinely unusual, something that will require explanation, something that might change how we understand these objects. The images also captured information beyond the obvious visual features. Brightness measurements allow astronomers to estimate how much dust is present in each jet. The colour of the light, determined by comparing images taken through different filters, reveals information about the dust particle sizes and potentially about the gas composition. The spatial distribution shows how material is flowing away from the nucleus, which directions are more active, how the jets evolve with distance from their source. Every pixel contains data, and extracting all that data takes time and expertise. One particularly valuable aspect of these Hubble observations is the resolution. From Hubble's orbital vantage point, the images can reveal structures much smaller than ground-based telescopes can typically resolve. This means seeing details in the jets, variations along their length, subtle features that provide clues about the physical processes at work. A ground-based telescope might show that a jet exists, Hubble shows the internal structure of that jet, the variations that tell you about how it's being produced and how it's evolving. The timing of the January 7th observation was also crucial. 3i Atlas was at a distance and activity level where it was bright enough to observe clearly, but not yet so close to the Sun that thermal constraints would limit Hubble's ability to point in that direction. Too close to the Sun and the scattered light becomes problematic, potentially damaging the telescope's sensitive instruments. There's a zone around the Sun that Hubble simply can't observe because the risk is too great. The observation was carefully scheduled to capture 3i Atlas at optimal conditions, maximising scientific return while staying within safe operational parameters. What makes these observations particularly valuable is context. This isn't the first time Hubble has looked at 3i Atlas. There have been previous observation campaigns as the comet approached the Sun, creating a timeline of how its activity evolved. The January 7th images can be compared with earlier data to track changes, to see what's new and what's persisted. That temporal context transforms individual observations into a story of evolution, showing how the comet responded to increasing solar heating as it journeyed through our solar system. Other telescopes have also been watching, of course. Ground-based observatories around the world have been tracking 3i Atlas, gathering spectroscopic data to analyse its chemical composition, monitoring its brightness changes, capturing their own images that contribute to the overall understanding. But Hubble's unique capabilities make its observations particularly valuable. The clarity, the resolution, the ability to see fine details that might be lost in ground-based observations blurred by atmospheric effects, all contribute to making Hubble data special. And when Hubble captures something unexpected, something that challenges existing understanding, the scientific community pays attention. The researchers analysing these images aren't working in isolation. They're part of a larger community of scientists studying this object from multiple perspectives, using different instruments, bringing different expertise. The Hubble team is comparing notes with spectroscopists analysing chemical composition, with theorists building models of comet behaviour, with dynamicists tracking the orbit and predicting future positions. It's collaborative work, each piece of the puzzle contributing to the larger picture. And that larger picture is still coming into focus. The January 7th images are remarkable, certainly. They've generated significant discussion and raised important questions. But they're not the end of the story. More observations are planned. Other telescopes will target 3i Atlas as it continues its journey. Each new dataset adds information, constrains theories, tests predictions. The process of understanding this object is ongoing, iterative, building confidence through accumulation of evidence from multiple independent sources. What Hubble actually saw on January 7th was an interstellar visitor in the full glory of its cometary display, jets streaming from its nucleus, gas and dust spreading through space, ancient ices sublimating under the sun's warming influence. It saw structure and pattern, activity and evolution, and it saw something that doesn't quite fit our expectations, a feature that points in the wrong direction, a geometric arrangement that demands explanation. The images are technically beautiful, scientifically rich, and deeply puzzling. They represent the best of what Hubble does, capturing data that advances human understanding while simultaneously revealing how much we still have to learn. Every great observation raises new questions even as it answers old ones. That's the nature of the enterprise. And the questions raised by these images are among the most intriguing we've encountered in studying visitors from beyond our solar system. Here's where we need to address what's really happening with that sunward-pointing jet. Because while it looks impossible at first glance, there's a phenomenon in cometary physics that offers a compelling explanation, one that doesn't require breaking any fundamental laws of nature. It's called an antitail, and understanding it requires thinking carefully about geometry, perspective, and how three-dimensional structures appear when we view them from a single vantage point. Let me start with a truth that might surprise you. That jet isn't actually shooting toward the sun. Material isn't defying solar wind and radiation pressure. Physics isn't being violated. What we're seeing is an optical effect, a trick of perspective created by the specific geometry of how Earth, 3i Atlas, and the Sun are positioned relative to each other at this moment in time. The material in that apparent sunward jet is actually moving away from the Sun, just like everything else being expelled from the comet. But from our viewing angle, it appears to point in the opposite direction. Think about how railroad tracks appear to converge toward a point on the horizon, even though they remain parallel. Or how a distant aeroplane can appear to be flying straight toward you when it's actually flying at an angle to your line of sight. Perspective creates optical illusions. Our brains interpret two-dimensional images and sometimes get the three-dimensional geometry wrong. The same principle applies to observing comets. We're viewing a three-dimensional structure projected onto a two-dimensional image, and that projection can create misleading appearances. Here's how an antitail forms. When a comet approaches the Sun and becomes active, it releases dust particles of various sizes. The smallest particles, microscopic grains, get pushed away from the Sun very efficiently by radiation pressure. They accelerate rapidly and form the bright, sweeping dust tail that can extend for millions of miles. But larger particles, grains that might be a millimetre or even several millimetres across, don't respond as strongly to radiation pressure. Their mass is higher relative to their surface area, so the same force that sends tiny particles flying has less effect on them. These larger, heavier dust particles still leave the nucleus. Outgassing carries them away into space, but their subsequent motion is dominated more by the comet's orbital velocity than by solar forces. They essentially inherit the comet's momentum, spreading out along the orbital path in both directions from the nucleus. Think of it like dropping breadcrumbs as you walk. The crumbs don't fly away from you, they fall roughly in place and mark your path. For a comet, these heavier dust particles mark its orbital path, creating a debris trail that extends both behind the comet where it's been and ahead of it where it's going. Now here's the crucial part. This orbital debris forms a flat sheet or disk, lying in the plane of the comet's orbit. Most of the time we view comets from an angle where we're looking down on or up at this orbital plane, so the debris sheet appears spread out, just part of the overall coma and tail structure. But occasionally, our viewing geometry becomes nearly edging to the orbital plane. When that happens, the entire sheet of debris compresses, from our perspective, into a narrow line. And that line can extend in any direction from the nucleus, depending on the exact geometric alignment, including toward the Sun. It's exactly like viewing Saturn's rings edging. When we're tilted relative to Saturn's equatorial plane, the rings appear magnificent spread across our view, obviously ring-shaped. But when Earth crosses through Saturn's ring plane, when we're looking at the rings precisely edging, they almost disappear, appearing as just a thin line across the planet. The rings haven't changed, they're still there, still the same structures. But our viewing angle has changed, and that change in perspective dramatically alters what we see. An antitail works the same way. The disk of orbital debris hasn't changed. The dust particles are still following the comet's orbital path, still spreading along that path in the expected way. But we've moved to a viewing position where we're seeing that disk edging, and the compression of perspective creates the appearance of a spike or jet extending from the nucleus toward the Sun. It's not really pointing toward the Sun in three-dimensional space. It's lying along the orbital path. But from our viewing angle at this specific time, those two directions happen to align, creating the illusion. This explanation has several things going for it. First, it doesn't violate physics. Solar wind and radiation pressure still behave exactly as expected. Dust still flows away from the Sun. Nothing impossible is happening. We're just seeing familiar behaviour from an unusual angle. Second, antitails have been observed before. They're rare, but they're documented. We have historical observations of comets displaying apparent sunward spikes that were convincingly explained as perspective effects. This isn't an ad hoc explanation invented specifically for 3I Atlas. It's an established phenomenon in cometary science. Third, the geometry is right. When researchers calculated the orbital positions of Earth and 3I Atlas on January 7th, when they determined the angle from which we were viewing the comet, the configuration was appropriate for an antitail to appear. We were close to the comet's orbital plane, viewing it at an angle where a debris disk would appear nearly edgeon. The geometric requirements for antitail visibility were satisfied. That's not proof, but it's consistent with the explanation. However, and this is important, not everything about the Hubble observations fits perfectly with the simple antitail interpretation. Antitails are typically subtle features, faint spikes that require careful observation to detect, and are often shorter than the main dust tail. What Hubble captured doesn't look subtle. The sunward feature is prominent, well-defined, and extends a considerable distance from the nucleus. It's not obviously fainter than the other jets. It has structure, variations along its length, characteristics that suggest it's more than just a sheet of debris viewed edgeon. There's also the question of composition. If the antitail is made of larger, heavier dust particles that weren't blown away efficiently by radiation pressure, we'd expect its colour and brightness properties to differ from the main dust tail composed of finer particles. Different particle sizes scatter light differently. The spectral properties should reflect that difference. Initial analysis suggests the sunward jet might indeed have different properties than the main tail, which supports the antitail interpretation. But the data isn't definitive yet. More detailed analysis is needed to really nail down the particle size distribution in that feature. Another consideration is stability. Geometric alignments that create antitail visibility are typically brief. As the comet moves along its orbit, and Earth continues its own orbital motion, the viewing angle changes. An antitail that's visible one week might disappear the next as the geometry shifts. If the sunward jet in the Hubble images is purely an antitail, we'd expect it to fade relatively quickly as the alignment changes. Monitoring observations over the following weeks should show that evolution. If the feature persists longer than the geometric explanation predicts, that would suggest something more complex is happening. There's also the possibility of a hybrid explanation. Maybe the feature is partly an antitail, with the geometric effect creating the basic appearance, but with additional factors influencing its prominence and structure. Perhaps 3I Atlas is producing an unusually large amount of larger dust particles, making the antitail more prominent than typical. Or perhaps there's an active region on the nucleus that's located in just the right place to enhance the antitail effect, ejecting material along the orbital path with enough velocity to make the feature more pronounced. Understanding antitails also requires understanding what they tell us about the nucleus. The fact that a comet produces larger dust particles in addition to fine dust reveals information about its surface properties and composition. The size distribution of ejected particles depends on how the surface material is bound together, how easily it fragments during the sublimation process, and what the original composition was. Interstellar objects might have different dust properties than solar system natives, shaped by their formation in different chemical environments and their different thermal histories. One particularly intriguing aspect of the antitail explanation is what it reveals about observation strategies. If we're seeing a geometric effect, that means other observers viewing 3I Atlas from different positions in the solar system might see something quite different. A spacecraft viewing the comet from a different angle wouldn't see the antitail at all, or would see it pointing in a different direction. This is one of the challenges of astronomy. We typically observe from a single vantage point, Earth or Earth orbit, and we have to infer three-dimensional structure from that limited perspective. Having multiple simultaneous views from different locations would dramatically improve our understanding. But that's rarely available. The antitail phenomenon also connects to the broader question of how we interpret astronomical observations. When we see something unexpected, something that appears to violate known physics, the first instinct should be to look for explanations within existing physical frameworks. Most of the time, the universe isn't revealing new physics. It's revealing new geometric arrangements or perspectives on familiar physics. The truly revolutionary observations, the ones that actually require rewriting textbooks, are exceedingly rare. Most anomalies resolve into mundane explanations once you have sufficient data and proper analysis. That's not to say antitails are boring. They're actually quite beautiful when you appreciate what's happening. You're seeing the ghostly trace of a comet's orbital path, marked by debris it left behind, compressed by perspective into a narrow spike that briefly appears before the changing geometry makes it vanish again. It's transient, fleeting, a reminder that our view of the cosmos is always filtered through the particular moment we happen to be observing and the specific position from which we're looking. Change that moment or that position, and the universe presents a different face. But there's still debate. Not all researchers studying the Hubble images are convinced that the antitail explanation fully accounts for what we're seeing. Some argue that the feature is too prominent, too structured, too persistent to be purely a geometric effect. They suggest that while an antitail component might be present, there could be additional factors at work. Perhaps 3 Atlas has unusual outgassing patterns related to its interstellar origin. Perhaps its nucleus shape creates unexpected shadow regions that affect how material is released. Perhaps there are volatile ices with different sublimation properties than we typically encounter in solar system comets. This ongoing scientific debate is healthy. It's how knowledge advances. Multiple researchers examining the same data, proposing different interpretations, testing those interpretations against further observations, gradually converging on the explanation that best fits all the evidence. The process takes time. It requires patience. Quick answers are rarely the right answers when dealing with complex phenomena, but eventually, through accumulation of data and refinement of models, understanding emerges. For now, the antitail explanation remains the leading candidate for understanding that puzzling sunward jet. It fits the geometry, it preserves known physics, and it has precedent in previous observations. But it's not a closed case. The prominence and structure of the feature still raise questions. The other jets and their geometric arrangement add layers of complexity that a simple antitail explanation doesn't fully address. And the broader mystery of what makes 3I Atlas different, what signatures of its interstellar origin we can detect in its behaviour, remains wide open. The antitail phenomenon gives us a framework for understanding one striking feature in the Hubble images, but it's part of a larger puzzle that we're still working to solve, piece by carefully observed piece. Let's step back and ask a deeper question. What makes 3I Atlas special? Why is this object generating so much scientific interest and so much careful observation? After all, we see comets regularly. Every year brings new cometary discoveries, fresh opportunities to study these icy travellers as they journey through the inner solar system. What makes this one different enough to warrant Hubble time and intensive analysis from research groups around the world? The answer comes down to 2 words: interstellar origin. 3I Atlas didn't form in our solar system. It's a visitor from beyond, an object that condensed from gas and dust orbiting a different star, shaped by conditions that might differ significantly from those that prevailed in our own solar nebula billions of years ago. When we study solar system comets, we're learning about our own origins, about the chemical and physical conditions that existed when our planetary system was forming. When we study interstellar comets, we're learning about other stellar systems, other planetary formation environments, diversity in the cosmos that we can't access any other way. Think about what this means. The galaxy contains hundreds of billions of stars. Each one potentially hosted its own planetary formation process, its own protoplanetary disk, where dust grains collided and stuck together, where ices condensed at different temperatures depending on distance from the star, where chemical reactions created complex molecules that eventually became incorporated into larger bodies. The details of these processes vary depending on the star's mass, its chemical composition, the properties of the molecular cloud from which it formed. Every stellar system is unique in some ways. For the most part, we can't directly sample material from other stellar systems. They're too far away. Interstellar distances are vast, almost beyond comprehension. The nearest star is over 4 light-years distant, and most stars are far more remote than that. We observe other stellar systems with telescopes, studying their light, detecting planets through gravitational effects or transit dimming, characterizing atmospheres through spectroscopy. But we can't reach out and touch material from those systems, can't bring samples back to our laboratories for detailed analysis, except when one of those distant systems ejects something. Planetary formation is a violent process. Gravitational interactions between growing planets scatter smaller bodies, flinging some into the central star, others into closer orbits, and some out into the outer reaches of the system or beyond. Every stellar system likely produces a population of these ejected objects, bodies that were formed in the protoplanetary disk but were kicked out by gravitational dynamics before they could accumulate into planets. They wander the galaxy, billions upon billions of orphaned fragments from planetary formation events scattered across space and time. Most of these interstellar wanderers drift through the darkness unnoticed, too small and too distant to detect. But occasionally, rarely, one of them passes close enough to our Sun that we can observe it. That's what happened with Oumuamua in 2017, the first confirmed interstellar object detected passing through our solar system. And that's what's happening now with 3I Atlas. These are opportunities to study material from other stellar systems without leaving home, cosmic gifts delivered to our doorstep by the random dynamics of galactic motion. But here's what makes 3I Atlas different from Oumuamua, and particularly valuable scientifically. Oumuamua didn't display obvious cometary activity. It didn't develop a coma or tails. It appeared inert, more asteroid-like than comet-like, though its behaviour was puzzling in other ways. That made it difficult to characterise. Without outgassing to study spectroscopically, without jets to reveal internal composition, researchers were limited in what they could learn. They could measure its trajectory, estimate its shape from brightness variations, analyse the sunlight reflecting off its surface. But they couldn't probe its chemical makeup in detail. 3I Atlas is different. It's active, vigorously so. The sublimation of ices is releasing gas that can be analysed spectroscopically to determine composition. The jets are revealing information about the nucleus structure and rotation. The dust being ejected can be studied to understand particle size distributions and material properties. This is a treasure trove of information, the kind of detailed data that allows real comparison between interstellar and solar system objects. For the first time, we can study an active interstellar comet and ask detailed questions about how it compares to comets formed in our own system. Early spectroscopic observations have already revealed intriguing information. The gas composition includes water vapour, as expected, along with carbon-based molecules like carbon monoxide and carbon dioxide. These are familiar species, the same kinds of molecules we see outgassing from solar system comets. But the relative abundances might be different. The ratio of carbon monoxide to water, for instance, appears higher than typical for solar system comets observed at similar distances from the Sun. That could indicate formation at colder temperatures, or a different chemical environment in the protoplanetary disk that produced 3I Atlas. These compositional differences, if they hold up under detailed analysis, are scientifically fascinating. They suggest that the stellar system where 3I Atlas formed might have had different properties than our own solar system. Maybe the star was cooler, allowing more volatile ices to condense closer in. Maybe the chemical composition of the original molecular cloud was different, enriched or depleted in certain elements compared to our solar nebula. Maybe the timescales of formation were different, affecting what chemical reactions had time to occur. Each possibility opens windows into understanding the diversity of planetary system formation across the galaxy. The jets themselves are another differentiating factor. While multiple jets aren't unheard of in solar system comets, the specific pattern displayed by 3i Atlas, that geometric arrangement we discussed earlier, is unusual. Whether this reflects something fundamental about interstellar objects or is just individual variation is unclear. We have a sample size of one actively outgassing interstellar comet. Drawing broad conclusions from a single example is scientifically dangerous, but it raises the question of whether nucleus structure or composition differences between interstellar and solar system objects might lead to systematically different outgassing patterns. There's also the matter of the orbit itself. 3i Atlas is on a hyperbolic trajectory, meaning it's moving too fast to be gravitationally bound to the Sun. It came from interstellar space, passed through our solar system, and will return to interstellar space, never to return. This is fundamentally different from periodic comets that orbit the Sun repeatedly, making regular appearances on predictable schedules. Periodic comets have been processed by their many approaches to the Sun, their surfaces modified by repeated heating and outgassing cycles, their most volatile ices potentially depleted. 3i Atlas, in contrast, is making its first and only passage near the Sun. Whatever ices were incorporated into it during formation have remained largely frozen and pristine during the millions or billions of years it spent drifting through interstellar space. The temperatures in the space between stars are close to absolute zero, just a few degrees above the cosmic microwave background. At those temperatures, nothing sublimated. Everything stayed frozen, preserving the original composition. This makes first-time visitors incredibly valuable scientifically. They're time capsules, preserving information about the conditions in their formation environment without the complicating factor of thermal processing from previous solar encounters. The journey itself is worth contemplating. 3i Atlas has been travelling through the galaxy for an immense span of time. We don't know exactly how long, but it was certainly millions of years and could easily be billions. During that journey, it experienced the galactic environment, exposed to cosmic rays that slowly modified its surface chemistry, occasionally passing close enough to other stars to feel weak gravitational perturbations, but mostly just drifting in the cold darkness. The galaxy has rotated multiple times during its journey. Stars have been born and died. Entire generations of planetary systems have formed. And through it all, this small icy body travelled silently, carrying within it the chemical fingerprint of its formation. Now, by random chance, its trajectory happened to intersect with our solar system. The odds of this happening for any particular interstellar object are astronomically small, but with billions of such objects drifting through the galaxy, occasional close encounters are inevitable. We were here at the right time with the right technology to detect it. We've had warning that it was coming, time to prepare observations, opportunity to study it during its brief passage through our neighbourhood. In cosmic terms, we've won a lottery, granted temporary access to material from beyond our system. But the window is closing. 3i Atlas is already past its closest approach to the Sun and moving outward. Every day it gets a little farther away, a little fainter, a little harder to observe in detail. By later this year, it will be too distant for most telescopes to detect, and then it will vanish back into the darkness, carrying its secrets with it, leaving us with whatever data we managed to gather during this brief encounter. We won't get another chance. This specific object will never return. And while we hope to detect other interstellar visitors in the future, each one is unique. Each one carries information from a different stellar environment. The opportunity to study 3i Atlas is fleeting and irreplaceable. This urgency drives the intense observational campaigns. Every telescope that can possibly observe this object is being scheduled for observations. Ground-based facilities, space telescopes, instruments across the electromagnetic spectrum are being brought to bear. Researchers are coordinating their efforts, sharing data, working together to extract maximum scientific return before the opportunity disappears. It's science operating at its collaborative best, driven by the recognition that this is a limited time offer the universe is extending, and we need to make the most of it. Why this visitor is different comes down to origin and opportunity. Origin because it formed somewhere else, under potentially different conditions, carrying chemical and physical signatures of another stellar environment. Opportunity because we have the chance to study it in detail, to gather data that can't be obtained any other way, to learn about the broader galaxy from this small piece of it that happened to pass close enough for us to examine. The triple jet pattern, the sunward antitail, the unusual activity level, all these features are part of what makes 3i Atlas fascinating. But the deeper significance lies in what this object represents. A messenger from beyond carrying information about corners of the galaxy we'll likely never reach physically, but can begin to understand through studying these rare visitors that random dynamics deliver to our cosmic doorstep. There's a clock ticking on our opportunity to understand this object. Right now, as you watch this video, 3i Atlas is moving away from the Sun at tremendous speed, heading back toward the outer solar system and eventually beyond into interstellar space. Every day that passes, it gets a little dimmer, a little harder to observe, a little more challenging to extract detailed data from. The race against time isn't a dramatic exaggeration. It's the reality of studying transient objects that don't wait around for our convenience. Think about the timeline. 3i Atlas reached its closest point to the Sun, perihelion, on October 29th, 2025. That moment, when the comet was most active, most intensely heated by solar radiation, represented peak observing season. The coma was at its brightest, the jets at their most prominent, the outgassing at its maximum. That was the moment when every telescope wanted to be looking, when the data quality would be highest, when we had the best chance of capturing detailed information. The Hubble observations we've been discussing came shortly after perihelion, timed to catch that peak activity. But cometary behaviour changes rapidly with distance from the Sun. As 3i Atlas recedes, solar heating diminishes following the inverse square law. Twice as far means 1/4 the heating intensity. The outgassing that created those spectacular jets will diminish, then fade, then stop entirely as the nucleus cools below the temperature where sublimation occurs readily. The coma will dissipate as gas molecules disperse into space and aren't replaced by new outgassing. The comet will fade from a prominent active object back to a faint, inert one. That transformation happens faster than you might expect. Within weeks to months, 3i Atlas will have faded significantly. By the time it crosses Jupiter's orbit, moving into the outer solar system, it will be a much more challenging observational target. And beyond that point, only the largest telescopes will be able to detect it at all. There's a window for detailed study, and that window is closing day by day. This creates intense pressure on observational astronomy. You can't postpone observations of a comet that's leaving. You can't wait for better weather or more convenient telescope scheduling. You have to observe when you can, grabbing data whenever the opportunity presents itself, even if conditions aren't perfect. Astronomers around the world are racing to gather as much information as possible, while 3i Atlas remains accessible. Ground-based telescopes are tracking it whenever it's above their horizon and weather permits. Space telescopes like Hubble have additional observations planned, trying to capture the evolution of the jets and coma as the comet continues outward. There's also a public engagement aspect to this timeline. In early January, there was an opportunity for amateur astronomers with moderately sized telescopes to potentially glimpse 3i Atlas, though the comet was already fading. The comet reached sufficient brightness that moderately sized instruments could detect it, at least as a faint fuzzy patch against the background stars. This was exciting for the astronomical community because it meant people around the world could personally participate in observing this interstellar visitor, could point their own equipment at the sky and capture photons that had bounced off an object from beyond our solar system. These public observing opportunities don't last long. Already, by the time you're watching this, 3i Atlas has faded beyond the reach of smaller amateur telescopes. Soon, only professional instruments will be able to track it. That makes the timing poignant. There was a brief window when this visitor from the stars was bright enough for anyone with the right equipment to see. Now that window is closing, and within months it will have closed completely. Future generations will learn about 3i Atlas from data and images, but they won't have the chance to observe it themselves. The scientific objectives during this critical observing period are focused and ambitious. Researchers want to continue monitoring the jets, documenting how they change as the comet cools. Does that triple jet pattern persist? Or does it evolve as different regions on the nucleus become more or less active? How does the antitail develop? Does it fade as the geometric alignment changes? Or does it persist longer than expected? These questions can only be answered by sustained observation over time, building up a timeline that reveals the comet's behaviour through different phases of its solar system passage. Spectroscopy is another priority. Different molecules outgas at different temperatures and different distances from the Sun. By continuing spectroscopic observations as 3i Atlas recedes, astronomers can map which volatiles are present and how readily they sublimate. Water ice dominates the outgassing close to the Sun. But farther out, more volatile species like carbon monoxide might become the dominant outgassing component. This compositional mapping provides information about how the nucleus is structured, what ices are mixed together versus separated into distinct layers, how the formation process organised materials within the comet. There are also dynamical studies ongoing. The comet's trajectory is being refined continuously as new position measurements come in. This isn't just academic interest in orbital mechanics. The trajectory tells us where 3i Atlas came from, what part of the galaxy it was travelling through before encountering our solar system. While we can't trace its path back to a specific stellar system, we can at least determine the general galactic direction from which it approached. That provides context about its journey and potentially about the stellar environments it might have passed relatively near during its long drift through space. One particularly intriguing study involves searching for additional fragments. Comets sometimes break apart due to thermal stress, rotational forces, or structural weaknesses. If 3i Atlas shed any fragments during its solar system passage, those fragments would be following slightly different trajectories, spreading out along the comet's orbital path. Detecting such fragments would provide additional targets for study and would also reveal information about the nucleus structure and cohesion. So far, no confirmed fragments have been detected, but searches continue. There's also coordination with observations at different wavelengths. Visible light observations show us reflected sunlight and scattered light from the dust coma, but comets also emit in infrared wavelengths thermal radiation from the heated surface and from the warm dust in the coma. Infrared observations can reveal information about temperature distributions and dust properties that visible light observations miss. Radio observations can detect specific molecular emission lines, providing detailed composition information. Ultraviolet observations can study gases in the coma that don't radiate strongly in visible light. Coordinating observations across these wavelength ranges requires scheduling multiple facilities, but the scientific payoff is enormous. Looking ahead, the final months of observations will be bittersweet. On one hand, there's satisfaction in having captured extensive data on this rare visitor, in having documented its properties and behaviour in unprecedented detail. On the other hand, there's the knowledge that this specific opportunity is ending, that we're saying goodbye to an object we'll never see again. By late in the year, 3i Atlas will have faded below the detection threshold of all but the most powerful telescopes, and eventually even those will lose track of it, as it becomes just another faint point among billions, invisible against the background of distant stars. The race against time also highlights the importance of preparedness. Our ability to study 3I Atlas in such detail exists because we have the infrastructure in place. Telescopes are operating, astronomers are trained and ready, data processing pipelines exist to handle the observations, international coordination mechanisms allow information sharing. This didn't happen by accident, it's the result of decades of investment in astronomical infrastructure and education, and it means that when opportunities like 3I Atlas arrive, we are positioned to take advantage of them. But it also reveals limitations. There are observations we'd love to conduct, but can't because the technology doesn't exist or isn't accessible. We'd love to send a spacecraft to intercept 3I Atlas, to study it up close, maybe even to return samples. But the short warning time and the difficulty of matching velocity with an interstellar object make that impossible with current propulsion technology. We'd love to have space-based telescopes across the solar system, providing simultaneous views from different angles, eliminating perspective effects and giving us true three-dimensional understanding. But we don't have that distributed infrastructure. We work with what we have, maximizing scientific return within the constraints of current technology and resources. The urgency also drives innovation. When faced with a unique opportunity that won't repeat, researchers find creative ways to extract information. They develop new analysis techniques, they push instruments to their limits, they collaborate across traditional boundaries. Science advances not just through routine work, but through these moments when something unusual appears and demands our attention. The race against time to study 3I Atlas is producing scientific papers, new insights, technological advances that will benefit future observations of other objects. The pressure of the ticking clock focuses effort and accelerates progress in ways that routine observing programs sometimes don't. As the window closes on detailed observations, the focus will shift to analysis. The data has been gathered. Now comes the painstaking work of extracting meaning from it, comparing with models, testing hypotheses, building comprehensive understanding. This phase is less visible than the observing campaigns, but it's equally important. Data without analysis is just numbers. Analysis transforms numbers into knowledge, into understanding, into the stories we can tell about this cosmic visitor, and what it reveals about the universe beyond our small corner of it. The race against time to observe is ending. The race to understand is just beginning. And that's a marathon that will continue long after 3I Atlas has vanished into the darkness from which it came. Let's talk about what we can learn from those jets. Because they're not just beautiful features to photograph. They're diagnostic tools, windows into the internal structure and composition of this ancient traveller. Every characteristic of a jet, its brightness, its shape, its evolution over time, tells us something about the nucleus from which it's emanating. It's detective work on a cosmic scale, reading clues written in gas and dust to understand an object we can't directly touch or probe. Start with the most basic question. Why do jets form at all? Why doesn't outgassing happen uniformly across the entire sunlit hemisphere of the nucleus? The answer lies in surface heterogeneity. Comet nuclei aren't smooth, uniform spheres of pure ice. They're irregular chunks of mixed material, ice and dust and rock all jumbled together, with different regions having different compositions and properties. Some areas might have more ice near the surface. Others might have thicker dust layers that act as insulation, slowing heat penetration. Active regions, where jets originate, are places where conditions allow efficient sublimation of ice once solar heating arrives. Think of it like springs emerging from a hillside. Water doesn't seep out uniformly across the entire slope. It emerges at specific points where underground aquifers reach the surface, where the geology permits flow. Similarly, jets emerge from specific points on the nucleus where the subsurface structure permits efficient gas release. Understanding where jets form and why tells us about the internal organisation of material within the comet. The triple jet pattern we've been discussing suggests 3 distinct active regions on 3I Atlas's nucleus, spaced at particular intervals around its surface. This could reflect the nucleus shape. If the body is elongated, The ends might heat differently than the middle, creating preferentially active regions. Or it could reflect composition variations. Maybe the nucleus formed from several smaller bodies that merged together, each with slightly different ice content, creating discrete active areas where ice-rich material reaches the surface. Rotation plays a crucial role too. As the nucleus spins, different areas rotate into and out of sunlight. An active region facing the sun heats up and produces outgassing, creating a jet. As rotation carries that region into shadow, it cools and the outgassing diminishes. Meanwhile, another region rotates into sunlight, and its activity increases. The result is a complex pattern, where jets turn on and off, strengthen and weaken, based on the rotation period and the location of active areas. For 3I Atlas, the persistence of the triple jet pattern across multiple observations suggests the active regions are long-lived and that the rotation period is conducive to keeping them visible. If the nucleus rotated very rapidly, jets might appear and disappear too quickly to produce the stable patterns we observe. If it rotated very slowly, we might only see whichever region happened to be facing the sun during our observations. The fact that we see 3 jets simultaneously suggests a rotation period and viewing geometry that allows all 3 active regions to contribute to the visible coma during the observation window. The brightness of each jet tells us about outgassing rates. A brighter jet means more material is being released, either because the active region is larger, or because it's more efficient at sublimating ice, or because it's currently receiving more intense solar heating. By measuring the brightness and comparing it with the expected solar heating at each location on the nucleus, researchers can estimate how efficiently different regions convert solar energy into sublimation. This efficiency varies depending on the ice content, the dust cover, and the thermal properties of the surface. The shape of each jet carries information too. Some jets appear narrow and collimated, maintaining a tight beam as they extend from the nucleus. Others are broader and more diffuse, spreading out rapidly. These differences reflect the subsurface structure where the jet originates. A narrow jet might come from a defined vent, perhaps a crack or fissure where gas can escape efficiently in a focused stream. A broad jet might come from a larger area where outgassing is happening across an extended region of the surface. It's the difference between water spraying from a nozzle versus flowing over a waterfall. Both are liquid in motion, but the geometry of the source creates very different flow patterns. Dust-Togas ratios are another valuable diagnostic. Sublimating ice releases gas that expands rapidly and flows away from the nucleus. This gas carries dust particles along with it, entraining the solid material in the outflow. But the efficiency of this process varies. Some regions might produce very dusty jets, with high ratios of dust to gas. Others might release mostly gas with relatively little dust. These differences reveal information about how dust and ice are mixed in the subsurface. If ice and dust are intimately mixed, the sublimation process efficiently drags dust along. If there are layers or pockets of relatively pure ice, the gas released might not entrain much dust. For 3I Atlas, preliminary analysis suggests the jets have different Dust-Togas ratios. One jet appears particularly dusty, producing a significant amount of solid material along with the gas. Another seems more gas-dominated. These variations are clues about the internal structure, suggesting the nucleus isn't homogeneous, but has regions with different compositions and mixing properties. And because this is an interstellar object, these compositional variations might reflect conditions in the protoplanetary disk where it formed, preserving information about chemical gradients and formation processes in another stellar system. The temporal evolution of the jets provides another layer of information. As 3I Atlas has approached and then begun receding from the Sun, the jets have changed. Some have strengthened as solar heating increased. Others have appeared and disappeared. These changes map out the thermal response of the nucleus, showing how different regions activate at different distances from the Sun. More volatile ices sublimate first, at greater distances where temperatures are still quite cold. Less volatile ices require closer approaches and higher temperatures before they sublimate efficiently. By tracking which jets are active at which distances, astronomers can infer the composition of different regions. If a jet turns on when the comet is still far from the Sun, it likely contains very volatile ices like carbon monoxide or nitrogen. If a jet only becomes prominent close to the Sun, it probably contains water ice, which requires higher temperatures to sublimate rapidly. The specific pattern of activation with solar distance is like a fingerprint, revealing the compositional structure of the nucleus layer by layer as heating penetrates deeper into the interior. There's also information in what we don't see. Some comets display rapid outbursts, sudden increases in activity where a jet dramatically brightens over short timescales. These outbursts can indicate structural changes, perhaps a layer of dust suddenly being blown away to expose fresh ice, or an internal pocket of gas suddenly finding a vent to the surface. The fact that 3I Atlas hasn't shown dramatic outbursts suggests a relatively stable structure, without large internal voids or dramatically insulated ice pockets waiting to suddenly activate. The jets also provide information about mass loss. By measuring the brightness and extent of the jets, and estimating the dust and gas production rates, researchers can calculate how much material 3I Atlas is losing during its solar passage. This matters because it tells us about the lifetime of such objects. Every approach to a star causes a comet to lose mass through sublimation. Do it enough times and eventually there's nothing left but non-volatile residue. Of course, 3I Atlas is on its first stellar approach, so it's losing pristine material. But the mass loss rate gives us insight into how many stellar encounters an object this size could survive before being depleted. One particularly fascinating aspect is comparing the jets of 3I Atlas with jets observed on solar system comets. Are they fundamentally similar, suggesting universal processes governed by the same physics? Or are there subtle differences that hint at compositional or structural variations between objects formed in different stellar environments? Early indications suggest more similarity than difference, which is both reassuring and slightly disappointing. Reassuring because it means our understanding of cometary physics, developed from studying solar system objects, applies broadly. Disappointing because we'd hoped to see dramatic differences that would reveal exotic compositions or unusual properties. But subtle differences might still exist, requiring careful analysis to detect. Small variations in gas production rates relative to dust, slight differences in the thermal response curves, unusual molecular abundance ratios. These could all be signatures of a different formation environment. The jets are providing the data needed for these comparisons, creating a detailed portrait of 3I Atlas's behaviour that can be quantitatively compared with the extensive database of solar system comet observations. What the jets tell us, ultimately, is that we're looking at a real comet, an object that behaves according to familiar physical principles, even though it formed somewhere else. The ices sublimate under solar heating. The gas carries dust away from the nucleus. Active regions produce jets. These are universal processes, not unique to our solar system. But within that universal framework, there's room for variation, for subtle differences that reflect different formation conditions and different chemical starting points. The jets are our primary tool for detecting those variations, for understanding not just that 3I Atlas is a comet, but precisely what kind of comet it is, and how its properties compare with the local population we're more familiar with. Every photon of light from those jets, every spectrum we capture, every image we process adds another piece to that understanding. As we reach the end of this journey through the mystery and science of 3I Atlas, I want to pull back and think about what this object means in a larger sense. Because beyond the technical details of jets and tails, beyond the puzzles of geometric patterns and perspective effects, there's something profoundly moving about what we're witnessing. We're watching an ancient fragment of another world, formed in orbit around a star we'll never identify, travelling through the galaxy for time spans that dwarf human civilization, happening to pass close enough to our sun that we can observe it for this brief moment before it continues on into darkness. That story, that cosmic scale, deserves recognition. Think about the journey, millions or billions of years ago, in a protoplanetary disk orbiting some distant star. Dust grains collided and stuck together. Over time, these aggregates grew, accumulating material, building up into larger bodies. Most of them eventually became parts of planets, swept up by the gravitational dominance of the largest objects in that forming system. But some, like the object we now call 3I Atlas, were flung outward by gravitational encounters, ejected from the system, before they could be incorporated into planets. This wasn't rare. Every stellar system probably produces a population of these wanderers, fragments of planetary formation scattered into the galaxy. And so it drifted through the Milky Way, moving at speeds typical of stars in our galactic neighbourhood, following a path shaped by the galaxy's overall gravitational field. It passed by other stars, usually at great distances, but occasionally closer. None were close enough to capture it permanently, to pull it into a new orbit. It remained a solitary wanderer, carrying its cargo of ancient ices through the space between stars. The galaxy rotated. Multiple full rotations, actually, taking hundreds of millions of years each. Stars died in supernovae, their cores collapsing and their outer layers exploding into space. Other stars formed from the enriched material. Generations of stellar evolution occurred while this small, icy body travelled silently through it all. And then, by random chance, its path happened to intersect with our solar system. The odds of any specific object encountering any specific stellar system are infinitesimally small. But with billions of interstellar objects wandering the galaxy and billions of stellar systems they might encounter, these meetings happen occasionally. The galaxy is so vast that even extremely improbable events occur somewhere at some time. We happen to be here when one occurred near us. We happen to have developed technology capable of detecting it. And we happen to be paying attention. That matters more than you might initially think. Even 100 years ago, 3I Atlas would have passed through our solar system completely unnoticed. We didn't have the telescopes to detect something so faint, nor the understanding to recognise it as unusual if we had glimpsed it. 50 years ago, we might have detected it as an anomalous object, but wouldn't have had the tools to study it in the detail we can now. The fact that we're living in this specific moment, when human technology has advanced enough to detect and characterise interstellar visitors, but still finds them rare and exciting enough to mobilise intensive study, is a remarkable coincidence of timing. This encounter teaches us about our place in the galaxy. For most of human history, we assumed our solar system was unique, or at least special. The idea that other stars might have planets is ancient, but confirmation only came recently. The discovery that planetary systems are common, that most stars probably host planets, revolutionised our understanding of cosmic architecture. But there's a difference between knowing intellectually that other stellar systems exist and actually examining material from them. 3I Atlas bridges that gap. It's a tangible connection to the broader galaxy, physical evidence that other stellar systems formed, evolved, ejected material just like ours did. And it reveals commonality. Despite forming in a potentially different chemical environment, despite travelling through interstellar space for eons, despite being shaped by a different star's radiation and a different protoplanetary disk's dynamics, 3I Atlas behaves fundamentally like solar system comets. Water ice sublimates under solar heating, dust gets entrained in gas flows, jets form from active regions. The physics is universal. The same natural laws that govern objects in our solar system govern objects from elsewhere. That might seem obvious, but it's actually a profound validation of our scientific understanding. The laws we've discovered through local observations apply beyond our local environment. The universe operates on consistent principles. But within that consistency, there's diversity. The compositional variations, the subtle differences in behaviour, the unusual geometric patterns, all suggest that while the fundamental physics is universal, the outcomes can vary depending on initial conditions. Just like planets in our solar system have similarities but also distinctive characteristics shaped by their formation locations and subsequent evolution, comets from different stellar systems might show both familiar behaviours and unique signatures of their origins. 3i Atlas appears to be showing us both, a familiar comet doing comet things, but with quirks and characteristics that hint at its foreign origin. This is what makes the study worthwhile beyond pure curiosity. Understanding the diversity of planetary formation conditions across the galaxy informs our understanding of how common habitable environments might be, how frequently chemical conditions suitable for life emerge, how varied stellar systems can be while still producing Earth-like worlds. Every interstellar object we can study adds data points to that larger question. We can't visit exoplanets directly, can't send probes to other stellar systems with current technology, but we can study the fragments of those systems when they happen to visit us. It's a slow way to build understanding, waiting for random encounters rather than actively exploring, but it's the method available to us now, and we make the most of it. There's also a poignant aspect to this encounter. We're watching something that's leaving forever. 3i Atlas will continue outward, past Jupiter, past Saturn, past the ice giants, eventually passing beyond the heliopause where the solar wind yields to the interstellar medium. And then it will simply drift, moving through the galaxy on a trajectory that will likely never again bring it close to any star for millions or billions of years. The brief flash of activity caused by its solar encounter will fade into memory, the coma will dissipate, the nucleus will return to its frozen state, and it will be alone again in the darkness. We had a moment with this traveller, a few months when it was close enough, bright enough, accessible enough to study. That moment is ending. Soon, 3i Atlas will be beyond the reach of our telescopes, returning to invisibility. Eventually, even the most powerful instruments will lose track of it, and then it will simply be gone from human knowledge, continuing its journey but doing so beyond our ability to observe. We'll have our data, our images, our measurements, but the object itself will have departed, carrying whatever secrets we didn't manage to extract during our brief time together. This temporary nature of the encounter adds urgency to the science, but it also adds meaning. We're not studying a permanent feature of our solar system that will always be available for future investigation. We're studying a visitor, making the most of the time we have, because we won't get another chance. Future generations will look back on this moment, will study our data, will wish they could have observed 3i Atlas themselves. We're the lucky ones who happen to be here at the right time. That's worth acknowledging and appreciating. It also points toward the future. 3i Atlas is only the second confirmed interstellar object we've detected passing through our solar system. As our telescopes improve, as our survey capabilities expand, we'll detect more. Already, new Olsky surveys are coming online specifically designed to catch fast-moving transient objects. The next interstellar visitor might be detected earlier, giving us more warning and more time to prepare observations. We might eventually achieve routine detection of interstellar objects, transforming them from rare curiosities into regular opportunities for study. That future isn't here yet, but it's coming. And the lessons we learn from studying 3i Atlas will inform how we approach those future visitors. So, what's the bigger picture? It's that we're part of a galaxy filled with stellar systems, many of which probably resemble our own in broad strokes while differing in details. Material escapes from those systems and wanders the galactic void, occasionally encountering other stars. We're now capable of detecting these encounters when they happen near us, of studying the wanderers in detail, of extracting information about their origins and comparing them with our local neighbourhood. Each encounter is unique, each visitor carries its own story, each dataset adds to our understanding of galactic diversity. 3i Atlas, with its puzzling jets and geometric mysteries and interstellar origins, is one chapter in this larger story. Not the first chapter, and certainly not the last, but a significant one, revealing both how much we've learned about these cosmic travellers and how much remains mysterious. As you continue through your day, as this video fades from your immediate thoughts, remember that above you, beyond the atmosphere and the obscuring glare of daylight, this ancient visitor is still there. It's moving away, fading, but still present, still carrying its cargo of frozen memories from another stellar system, still displaying those jets that puzzled scientists and sparked the investigation we've been discussing. Eventually, it will be gone. But for now, for this brief moment in cosmic history, we share the solar system with a traveller from beyond. That's remarkable. That's worth pausing to appreciate. And that's why scientists around the world have devoted their time and their careers' most sophisticated instruments to studying it. Because opportunities like this don't come often. Because the universe has handed us a gift. And because we're curious enough, dedicated enough, awestruck enough to accept that gift and learn everything we possibly can from it before the moment passes and the traveller continues on its eternal journey through the stars. If this journey through cosmic mystery has resonated with you, if you've found yourself captivated by the story of this ancient wanderer and the puzzles it presents, do me a favour. Share this video with someone who looks up at the night sky and wonders what's out there. Subscribe to this channel if you want to continue exploring the universe's secrets together, and leave a comment telling me what aspect of 3i Atlas fascinated you most, or what question you still have about this interstellar visitor. Your engagement, your curiosity, your willingness to spend time learning about objects millions of miles away that you'll never touch, that's what makes science communication worthwhile. That's what drives the sharing of knowledge and the collective sense of wonder that unites us all as inhabitants of this small planet looking outward into the vast cosmos. Thank you for staying with me through this deep dive. Keep looking up, keep questioning, keep exploring. The universe has more mysteries waiting, and we'll uncover them together.